Hello, good evening, students. I hope you all are fine. So, in the last class, we have seen primary waves and secondary waves. So, in today's class, we will see the earthquake hazards in India. So, I'm sharing the screen. Hope it is visible to you. Types of seismic waves we have seen in the last class. It's characteristic of earthquakes. This also we have started. So, different zones also we have seen. This we left. That is place, depth, date, time, and year, magnitude, and epicenter. So starting with Indian Ocean, which is greater than the death toll is 283,106, date, time, and year 850 December 26, 2004. So magnitude is 9.3. West coast of Sumatra, Indonesia. So in the Indian Ocean, it started. Indian Ocean. The death toll is more than 2,83,106, and the date was 850 December 26, 2004. And the magnitude of earthquake was 9.3, and the epicenter was west coast of Sumatra, Indonesia. Next was Kashmir. So the death toll was 1,30,000, and the date, time, and year is 850 October in 2005, and the magnitude is 7.6, and the epicenter was Muzaffarabad. Next, Bihar and Nepal, greater than 30,000. And the date, time is 14 or 13th January. Date, time was 14/9 to 13. January 15, 1934. And the magnitude of the earthquake was 8.7. South of Mount Everest. Gujarat, 20,000 deaths were recorded. Time was 8:50, January 26, 2001. 2.7.7. Kutch, Gujarat. Kangra, greater than 20,000, more than 20,000. Time 6:10, April 4, 1905. Magnitude 7.8, Himalayas. Lattur, that tool is more than 9748. Date is date no time is 10:25 September 30 1993. Magnitude is 6.4 Killer in Latur. Assam, that is 1526. Time is 7:39 August 15 1950. Magnitude is 8.6. Epicenter is Rima, Tibet. Assam 1500. Time is 5:50. It's June 2 in the 1897. And the epicenter is 8.1. Exact location not known. Earthquake risk evaluation and mitigation. Evaluation already we have stated that it is how it is measured in terms of magnitude intensity by using seismographs. Mitigation of earthquake is of prime importance. Protecting against earthquake damage. Prepare a seismic map for the globe which identifies rock types, liquefaction potential, landslide potential. Extensive geological surveying has to be done to identify all active faults, including hidden faults. Earthquake resistant design of structure. Enact building codes to design and build earthquake resistant structure in high seismic risk areas. Wood, steel, and reinforced concrete are preferred as they tend to move with shaking ground. Unreinforced concrete and heavy masonry tend to move independently and in opposition to the shaking, battering one another until the structure collapses. To structural behavior under gravity and seismic load. Gravity load, lateral load. Direction of load vertical, direction of load horizontal. So gravity load and lateral load, how we are differentiating? Direction of load is vertical, whereas lateral load, the direction of load is horizontal. Direction of direction imposed on the structure. Next, reversible in nature and cyclic. Next, deterministic load, not deterministic, not easy to estimate. Do not produce fatigue due to cyclic in nature produces fatigue. Fatigue meaning stress person due to cyclic loading. In case of gravity load, drift and deformation are small. Whereas in case of lateral load, drift and deformation are large. Structural shows inelastic behavior under seismic load. In flexural members, bending moment and central position is hogging, negative, and at ends it is sagging. In flexural members, alternatively sagging and hanging moment occurs. A structure shear force is smaller in comparison of seismic load. Shear force is larger than gravity load. Column subjected to axial forces and less bending moment than seismic load. Column is subjected to more shear forces and building behave as cantilever. Tensile force at side of seismic force and opposite side there will be compression force in column. So gravity load, lateral loading, bending moment and shear force diagram. This is lateral loading. Lateral load resisting structural system. There are basically three lateral force resisting system. They are moment resisting building frame system, shear wall or bare wall system, bearing wall system, and dual system. So first is moment resisting building frame system. So what is moment resisting frame? It is a rectilinear assemblage of beams and columns with beams rigidly connected to the columns. So what is moment resisting building frame system? Moment resisting frame is a rectilinear assemblage of beams and columns with the beams rigidly connected to the columns. Next, resistance to lateral force is provided primarily by rigid frame action, that is by the development of bending moment and shear force in the frame members and joint. By virtue of the rigid beam column connections, a moment frame cannot displace laterally without bending the beams or columns depending upon the geometry of the connection. The bending rigidity and strength of the frame members is therefore the primary source of lateral stiffness and strength for the entire frame. Moment resisting frame used for both structural steel and reinforced concrete construction. The horizontal beams and vertical columns provide both support for the structure's weight and the strength and stiffness needed to resist lateral forces. Stiffness and strength are achieved through the use of rigid connections between the beams and columns that prevent these elements from rotating relative to one another. Movement resisting frame systems are popular because they do not require braced frames or structural walls, therefore permitting large open spaces and facets with many unobstructed window openings. Shear wall or bearing wall system. Shear walls take lateral loads placed on it by the building itself, as well as the lateral loads experienced if and when wind hits the structure and in some instances earthquake. So what is happening in case of shear wall or bearing wall system? Shear wall takes lateral loads. Shear wall क्या करते हैं? Lateral load लेते हैं, placed on it by the building itself, as well as the lateral load experienced if and when wind hits the structure and in some instances earthquake. Bearing walls are just that, bearing the weight of elements, beams, girders, building components attached to it. So this is the shear wall. It is taking the horizontal load which is acting on it. Dual system. A dual system is a structural system in which an essentially complete frame provides support for gravity loads and resistance to lateral loads is provided by specially detailed moment resisting frame and shear walls or braced frame. Both shear walls and frames participating in resisting the lateral loads resulting from earthquakes or wind or storms, and the portion of the force is resisted by each one depends on its rigidity, modulus of elasticity, and its ductility, and the possibility to develop plastic hinges in its parts. The moment resisting frame may be either steel or concrete, but concrete intermediates frame cannot be used in seismic zone terrain. The moment resisting frame must be capable of resisting at least 25% of the base shear, and the two systems must be designed to resist the total lateral load in proportion to their relative rigidity. So this is the dual lateral load system, where wall frame dual system hold lateral frames 25% of lateral load minimum. Requirements of requirements of efficient earthquake resistant structural system. The building and its superstructure should be simple, symmetric, and regular in plan and elevation to prevent significant torsion forces. जो बिल्डिंग है वो उसका सुपरस्ट्रक्चर, द बिल्डिंग एंड इट्स सुपरस्ट्रक्चर शुड बी सिंपल, symmetric and regular in plan and elevation. Plan or elevation, the building का simple रहना, the building and its superstructure. The building and its superstructure should be simple, symmetric, and regular in plan and elevation to prevent significant torsion forces. The building and its superstructure should have uniform and continuous distribution of mass, stiffness, strength, and ductility to avoid the overstressing of structural component due to stress concentration. So if you see here, this is the substructure, and this is the superstructure, and this is your roof, second floor, ground floor. The structure should have good lateral load resisting structural system and direct pathway without discontinuity. The structure कैसा रहना? It should have good lateral load resisting system and direct pathway without discontinuity. Integral action of soil, foundation, superstructure system. The different elements of the substructure and superstructure system should be rigidly connected together so that they can work as a single unit. The superstructure should be provided with compatible stiffness and strength between its member connections, supporting foundation, and so on. The superstructure should be detailed for adequate ductility so that elastic deformations can be controlled to develop plasticity. The structure should be able to dissipate seismic energy by the yielding of its component. The building should be light and should avoid unnecessary masses because the larger the mass, the more will be the seismic forces. The superstructure should not have long cantilever to avoid large deformation. Damping devices base isolation system. So what is damping an earthquake? The study of decrease of successive amplitude of vibration of a structure by the dissipation of energy is known as damping. So how we are defining damping? The study of decrease of successive amplitudes of vibration of a structure by the dissipation of vibration energy is known as damping. Damping को कैसे define कर रहे हैं? The study of decrease of successive amplitudes of vibration. The study of decrease of successive amplitudes of vibration of a structure by the dissipation of vibration energy is known as damping. Viscous dampers. In viscous dampers, seismic energy is absorbed by silicon-based fluid passing between piston cylinder arrangement. Viscous dampers are used in high-rise building in seismic areas. It can operate over an ambient temperature ranging from 40 degrees Celsius to 70 degrees Celsius. Viscous damper reduces the vibration induced by both strong wind and earthquake. Viscoelastic dampers. Another type of damper is viscoelastic damper that stretch an elastometer in combination with metal parts. This type of damper dissipates the building's mechanical energy by converting it into heat. Several factors such as ambient temperature and the loading frequency affect the performance and consequently the effectiveness of the damper system. Viscoelastic dampers have been successfully incorporated in a number of tall buildings as a viable energy dissipating system to suppress wind and earthquake induced motion of building structure. Friction dampers. How you will define friction dampers? Generally, friction damper device consists of several steel plates sliding against each other in opposite direction. The steel plates are separated by shims of friction pad material. The damper dissipates energy by means of friction between the surface which are rubbing against each other. It is also possible to manufacture surface from materials other than steel. So what is base isolation? A base isolation system is a popular system implemented in a structure to protect it from the action of seismic forces. This system as base isolation bearing was developed by Dr. Bill Robinson in the 1970 in New Zealand. A base isolation system is used as a damage resistant seismic design solution for both new and retrofitted buildings. This system is hence named as seismic base isolation system. Working principle of base isolation system. The fundamental principle of a base isolation system is to alter the response of the building structure so that the ground below it can move easily without transmitting these motion forces to the building structure above. This is achieved by separating or isolating the superstructure from its substructure that is resting on a shaking ground. Thus, the structure has less effect due to earthquake forces. The term isolation itself refers to the reduced action between the main structure and the ground. When the system is provided under the substructure, it is called base isolation. The base isolation system comes under passive vibration control technology and earthquake engineering. It is a design strategy that serves the purpose of uncoupling the structure from the damaging effects of earthquake ground motion. The decoupling action of the base isolation makes the building behave more flexible, thus increasing its resistance against the earthquake. The principle can be more clearly explained by considering an example. Consider a building resting over frictionless rollers. When the ground below the building is subjected to shaking, the rollers start to freely roll, but the building stays above without any movement. So what is happening? अगर समझो एक ग्राउंड है, the ground below the building, एक बिल्डिंग है उसके नीचे का ग्राउंड subjected to shaking. When the ground below the building is subjected to shaking, the rollers start to move freely, but the building stays above without any movement. लेकिन बिल्डिंग क्या है जिसके ऊपर रहती है विदाउट मूवमेंट मूव हो सकती है. Locations of base isolators in building. Generally, the isolators are installed at the top or bottom or mid-height of the building basement columns and the walls. If not, a diaphragm is immediately placed above the isolator. The placement of base isolator must be done in such a way that the building must be able to move horizontally relative to the below ground surface for a distance not less than 100 mm. Okay. So this the building shows below shows the possible locations of base isolator near the substructure. So if you see here under foundation, isolator is provided here. New foundation is provided in this way. On foundation. So the new foundation beam is here, whereas the isolator is here. At a basement column, isolator is here. Separation of exterior wall is here. At a middle story column, isolator is here. Location of base isolator in buildings. Generally, the isolators are installed at the top or bottom or mid height of the building basement's column and the wall. If not, diaphragm is immediately placed above the isolator. Generally, the isolators are installed at the top or bottom or mid-height of the building basement column and the walls. If not, a diaphragm is immediately placed above the isolator. The placement of base isolator must be done in such a way that the building must be able to move horizontally relative relative to the below ground for a distance not less than 100 mm. See here, the placement of base isolator must be done in such a way that the building must be able to move horizontally relative to the below surface for not less than 100 mm. So this figure shows the possible locations of base isolator near the substructure. So the sub isolator is provided here in center foundation, whereas on foundation the isolator is provided here, whereas the new foundation beam is provided here. At a basement column, the isolator is provided here. Separation of exterior is here. At a middle story column, the isolator is provided here. So this completes our topic. So I'm just stopping the share option. So I'm sharing the screen. Hope it is visible to you. So the response history and strong motion characteristic. So what are the factors we need to study in this module? Number one is response history and strong ground motion. Response history and strong motion characteristics we need to study. Next, we need to study response spectrum, elastic and inelastic response spectra, tripartite EVA response spectrum, use of the response spectrum in earthquake resistant design, computation of seismic forces in multi-story building using procedures equivalent analysis and dynamic analysis. Introduction part. For the design of structure to resist earthquake, it is necessary to have some knowledge of ground motion. So for the design of structure to resist earthquake, what is necessary? It is necessary to have some knowledge of ground motion. During earthquake, the ground movement is very complex, producing translation in any general direction combined with rotation about arbitrary axis. Earthquake motion can be recorded in terms of ground displacement, velocity, or acceleration. So strong ground motion. Strong ground motion as the strong earthquake shaking that occurs close to less than about 50 kilometers from a positive fault. The strength of the shaking involved in strong ground motion usually overruns a seismometer, forcing the use of accelerographs or strong ground motion accelerator for recording. The strong ground motion is recorded with the help of accelerometer. When the natural frequency of the instrument is very high compared to that of the vibration to be measured, the instrument picks up the acceleration of the motion measured. A component trace of acceleration is also known as accelerogram. An accelerogram is a time history of acceleration composed of non-periodic sequence of acceleration pulses. It shows three traces of acceleration, one as longitudinal, one as vertical, and one as transverse. The area under acceleration pulse is a measure of vibration transmitted to the structure with the foundation on the ground. The amplitude is of the pulse is often taken as the measure of severity of ground shaking, which could be termed as satisfactory if the duration of all pulses are similar. The temporal evolution of accelerogram is composed of three parts: rise, strong motion, decay. The ground velocity and displacement can be obtained by direct integration of accelerogram. So how we are doing? The area under acceleration pulse is a measure of vibration transmitted to the structure with foundation on the ground. Next, the amplitude is of the pulse is often taken as the measure of severity of ground shaking, which would be termed as satisfactory if the duration of all pulses are similar. The temporal evolution of accelerogram is composed of three parts: rise, strong motion, decay. The ground velocity and displacement can be obtained by direct integration of accelerogram. Strong motion arrays in India. Starting from 1976, Department of Earthquake Engineering, Indian Institute of Technology, Roorkee, operated a network of about 200 analog strong motion accelerogram covering parts of Himachal Pradesh, Punjab, Haryana, Uttaranchal, Uttar Pradesh, Bihar, West Bengal, Sikkim, and northeastern India. So what they did, starting from 1966, 1976, Department of Earthquake Engineering, Indian Institute of Technology, Roorkee, operated a network of about 200 analog strong motion accelerographs covering parts of Himachal Pradesh, Punjab, Haryana, Uttaranchal, Uttar Pradesh, Bihar, West Bengal, Sikkim, and Northeast India. So the ground motion characteristics include the literature for the quantitatively describing the various characteristics of the ground motion. These cover property characteristics such as amplitude of motion, frequency, content of motion, duration of motion, etc. The three motion parameters, that is peak ground acceleration value, response spectrum, and acceleration time history of a site commonly used the design of a structure are known as design basis ground motion parameter (DBGM) parameters. Peak ground acceleration. So how you will define peak ground acceleration? The peak ground acceleration is a measure of maximum amplitude of motion and is defined as the largest absolute velocity of acceleration time history. Generally, at distances several source dimensions away, vertical PGAs are found to be less than the horizontal PGA, though at near source distance it could be equal to higher than the corresponding horizontal PGA. For engineering purpose, vertical PGA is assumed to be two-thirds of horizontal PGA. Peak velocity. Peak velocity is the largest absolute value of velocity time history. It is more sensitive to the intermediate frequency components of motion and characteristics characterizes the response to structure that are sensitive to intermediate range of ground motion. Example, tall building, bridges, etc. Peak velocity. Peak displacements reflect the amplitude of lower frequency components in ground motion. Accurate estimations of these parameters is difficult as the errors in signal processing and numerical integration greatly affect the estimation of amplitude, displacement, and time history. Frequency content of motion. Earthquake ground motion is an amalgamation of harmonic motion with a range of frequency component and amplitude. Several approaches have been proposed in the literature to quantitatively estimate these characteristics. Some of these are discussed below. The spectral velocity and spectral relation are related by SA is equal to gamma naught into S into A, where S is the spectral acceleration, SV is the spectral velocity, gamma naught the natural frequency. Similarly, it can be shown that SV equal to omega naught into SD, where SD is the spectral displacement. So I hope you have understood. If you have any doubt, you can just make the drop in answer in the comment box. You can email me at abhimandir@gmail.com. You can even call me during evening hours at 8553171859. I hope we have understood the concept. We will continue in the next class. Thank you, friends. Have a nice day.